I never thought we'd sell 40 pieces.
We still have a lot left.
That's okay. My tita promised she'd buy what's left. So, how much money did you make?
Let's see. We made 250 pesos.
If tarts cost 5 pesos and brownies cost 10 pesos, how much of each pastry did we sell? So how much of each type of pastry were they able to sell?
That's a tough one.
Well, the problem can be simplified if we use mathematical symbols.
Oh, I see. We could let X be the number of tarts sold and Y be the number of brownies sold.
So what equation corresponds to the total number of pastries sold?
Well, since they sold 40 pieces, X plus Y should equal 40.
And we can write total sales as 5x plus 10y is equal to 250. Since each tart X costs 5 pesos and each brownie Y costs 10 pesos.
Excellent! Notice that you just ended up with two linear equations, or as I've said, a system of linear equations. Finding the ordered pair x and y that will satisfy both equations is the same as finding the solution to the system.
Oh, I get it! X is equal to 20 and Y is equal to 20 is a solution for the first equation but not for the second. So, X is equal to 20 and Y is equal to 20 is not a solution to the system. But how do we find the values of X and Y that will satisfy both equations?
Does anyone have any idea?
How about we try graphing the two equations?
That's a good idea. Would anyone like to try?
I'll do it, ma'am. Let's see. In the first equation, if X equals 0, Y equals 40. And if Y equals 0, X equals 40. So the line goes this way. In the second equation, if X equals 0, Y equals 25. And if Y equals 0, X equals 50. So the line goes this way. Hey, the lines intersect at 3010. What does this mean, ma'am?
Why don't you try substituting these values in the two equations?
Ma'am, let me do it.
Go ahead.
Okay, so if x is equal to 30 and y is equal to 10, hey, it satisfies both equations. That means that they sold 30 tarts and 10 brownies.
Oh, so the intersection of the lines in a system of linear equations is the solution to that system.
That's right.
Ma'am, but what if the lines don't intersect? Does this mean that the system has no solution?
Yes. And what do we call lines that don't intersect?
Parallel lines!
So, a system composed of parallel lines has no solution. Now, consider the following system. Would someone like to graph these?
I'll do it, ma'am. So, in equation 1, if X equals 0, then Y equals 2. And if Y equals 0, then X equals 4. So the line goes this way. In equation 2, if X equals 0, then Y equals 2. And if Y equals 0, then X equals 4. So the line goes this. Hey, the lines overlap.
Oh yes, and we say that these lines coincide.
Oh.
In our previous problem, the two lines had one point in common, meaning they intersected in one point. How many points in common do our two lines have?
A lot, maybe infinite. For example, there's 0 and 2, 2 and 1, 4 and 0, and 6 and negative 1.
You're right. They have an infinite number of points in common. And does each one satisfy both equations in the system?
They should. There are points on both lines.
That's correct.
Ma'am, does this mean when the lines of a system overlap, there is more than one solution to the problem?
Of course. Actually, when the lines of a system coincide, the system has an infinite number of solutions. Now, let's organize what we've learned. What can you say about the graph of a system with regard to the number of points in common and the number of solutions to the system?
Well, if the lines in a system intersect, they have a point in common, and thus only one solution.
And if the lines coincide, they have an infinite number of points in common, and thus an infinite number of solutions.
And if the lines are parallel, they have no points in common, and thus no solution.
Very good, class. These three types of systems have names. If a system has a single solution, it is called an independent system. If a system has an infinite number of solutions, it is called a dependent system. These two cases can also be called consistent systems. However, if a system has no solution, it is called an inconsistent system.
Ma'am, I just realized something. We don't always have to graph the system to know if it's consistent or not. That will save us a lot of time in tackling a problem.
That's an excellent observation.
How do you do that?
We can rewrite the equations in slope-intercept form. For example, consider the following systems. If we rewrite the equations in the slope-intercept form, we end up with these versions of the systems.
Oh, I see. In the first one, we end up with lines with different slopes, so they should intersect at one point.
And look, in the second system, the slopes and y-intercepts are the same, so the lines must coincide. So the system has an infinite number of solutions. We don't need to graph it.
Oh, and in the third one, we have lines with equal slopes but different y-intercepts. So the lines must be parallel. So the system has no solution.
Very good, class, but you missed something.
What?
Take a look at the equations of the lines which coincide.
Oh, I see. One equation is a multiple of the other. Look, if you multiply equation 1 by 3, you end up with equation 2.
That's correct. So, we can say that if one equation is a multiple of another, the graphs of these two equations coincide.
So in this case, the system has an infinite number of solutions.
Of course! Good job, class! So, what have we learned today?
We learned how to determine if two lines are parallel or perpendicular using their slopes.
We also learned how to solve a system of linear equations by graphing.
We also found out that we don't need to do that if we know that the system is dependent or inconsistent.